So we have these values, these numbers, and this list that represent the hierarchical structural action of the hyperbolic figure eight knot. Great. We'll move on now to chapter 5. And in, what is it, one page or do we 2 pages? 2 pages. We're going to now completely switch directions. So far we've been talking about geometry, right? Just geometry. There's been no actual connection to the physical real world. We're just defining the simplest possible geometric balance, and we're being nitpicky about defining every single balance individually. So we've divided it, decomposed it into its individual balances, right? Well, things are about to change. Chapter 5, the boundary conditions of physical reality. The boundary conditions that maintain the balance of the hyperbolic figure eight knot define the boundary conditions of physical reality. The measured limits of time, space, charge, mass, and temperature, known as the Planck constants. And I mean this directly and literally. Every persistent external rotation of the hyperbolic figure eight knot, which we just defined, multiplied by a boundary doubling in each case, raised to the number of hinges synced to that rotation, defines a bound of physical measure, a Planck constant. So let's look at the bottom here, the Planck time. The minimum possible time available, not just because of our limits in technology right now, available in nature, we have found is equal to 5.391247 plus or minus 60 in the 47 times 10 to the negative 44 seconds. And here, in our geometric structure, in our balance decomposition representation of the hyperbolic figure eight knot, the minimum possible balance, we find that the minimum expression in that balance happens to be equal to 5.39125836832331 and on and on and on times 10 to the negative 44. It's exactly within the error bars of our best known measurement for the Planck time. And in every single case, the 5 dimensions that make up our physical reality, the measured limits of each dimension is predicted by, and now to any digit you want, the structure of the hyperbolic figure eight knot. Just look at this on one page. Those 5 rotations define the 5 boundaries of physical action in reality, the 5 dimensions of our universe, the boundary conditions of reality. It's beautiful. And now, that means we know these values theoretically. Right? We now know the Planck mass. We know what its true number is, what its true expression is, and why. Beautiful. We know what all of these are. But what does this really do for us, other than explain the Planck values, which have had no story or no explanation until now? What else can this really do? Well, let's see. You might have a suspicion at this point that now that you've framed the boundary conditions of reality, we can really do some physics. Since, if you've had any physics background training, you know that physics is generally something that's defining a system, defining its boundary conditions, and then you're basically done. Once you've finished defining your boundary conditions, you know what the system's going to do. Right? Well, we've never had the boundary conditions of reality before. Here, we've just got a simple, single geometry that perfectly, identically, geometrically, and numerically predicted perfectly the conditions of every limiting measure of our physical reality. Fantastic. The hyperbolic figure eight knot defines a bounded arena composed of 5 persistent kinds of measure. We're going to call them time, space, charge, mass, and temperature, just to go along with our historical tradition, okay? But it doesn't matter what we call them. The point is that there's 5 persistent kinds of measure whose boundaries are the Planck constants. The Platonic form of persistence, the simplest possible self-balanced manifold, elegantly and uniquely defines the stage of reality. I think this is more elegant than words can ever approach. Look at this system. The simple inside-outside balance that we're maintaining here gives us a partitioning that defines the Planck time, the Planck length, the Planck charge, the Planck mass, and the Planck temperature as the grandest reach of each of those 5 actions. Chapter 6, the hyperbolic vortex. All right, we're not very far off from all the math you really need to put everything together, right? We've gotten the decomposition structure of the 5 actions. Now, I want to talk about all the possible expressions of charge and mass in this balance. So the external Planck charge boundary and Planck mass boundary are connected, of course, right? You see that they're always bound. But I want to know how many possible ways can they be divided up? How many ways can we divide up this charge and mass boundaries, right? These 2 actions are in play, they're in motion together. So how many partitions are available in this action? All right, well, to do this, we start with recognizing that the 2 external boundaries, the hyperbolic figure 8 knot, the Planck charge and the Planck mass boundaries, connect via the hyperbolic vortex equation. Now, I know if equations aren't your thing, try to suspend that for this one, because this is one of the most beautiful equations you will ever see. I mean, honestly, this whole book is literally the list of most beautiful equations you'll ever see. First, you start with just the unit hyperbola equation, 1 over x plus x cubed. Okay, you set it equal to whatever you want, depending on the scaling you want to make this thing. Instead of just having the hyperbola equation, modify it so that the third one gets wrapped around a circle. Okay? So it's almost the same as the equation you're so comfortable with doing a hyperbola, just the base hyperbola, okay? And I'm using je instead of x, but it's just a variable. When you set that structure up, instead of a hyperbola, you have a hyperbola whose third component is wrapped around a circle. The component that's not a simple inverse of the other, right? So 2 components are just inverses of each other, really awesome. And the one that's not is wrapped around a circle. Cool. Well, now that we have that structure just geometrically arranged, we just define a relationship. We have 2 things that are opposites and one thing that's cubed and wrapped around a circle, right? But we're going to set that equal to the geometric action of our hyperbolic vortex, which, as you can probably guess, is twist and twist, 2 different orthogonal direction twists. So 90-degree twist one way, simultaneously at the same time, right? 90-degree twist another way. Okay, you can write this as e to the negative pi over 2 and then raise that negative pi over 2, or e to the negative pi over 2 is equal to I to the I, so I'm going to write it like that. So 2 twists of negative pi over 2. Minus the boundary you're twisting around. So wherever your 0 is, your 0 line. Well, since we're talking about the action, the hyperbolic vortex that connects the boundaries of the charge and mass boundaries in our hyperbolic vortex action, right? So we're going to subtract the Planck mass boundary from our equation. Very simple, elegant. We're just taking a hyperbola, a unit hyperbola, wrapping one component around a circle, and setting this construction equal to 2 twists around a 0 boundary, specifically the Planck mass boundary. Now, when we do this, we can just put in the computer and solve for our variable, and we get the partitions of this arrangement. We get the solutions. So this connection partitions into 4 solutions, right? It's a cubic term, so it has to have at least 3. It has 4, and they're composed of 6 parts, 4 real and 2 imaginary. If this is a completely new topic to you, try to follow along. We're saying that the geometry of that equation divides things up into segments that have a slice of this first number, je1, 0.08542, on, and je2, and je3, and je4. So simultaneously, all of those values, every one of those numbers, you could plug into our equation up there as je, and it would give you the correct answer, right? So all 4 of them are perfectly valid solutions, which means they represent all of the natural partition divisions that are now balanced between the Planck charge and the Planck mass boundaries. They represent the way we divide up charge and mass. Very important. Great. These solutions have ideally cyclic combinatorics. This is something we really should spend some time on. I kind of blow through it because I really want somebody to see the elegance here. So I would try to streamline and make it short. But let's pause for a second. If you take those 4 solutions, you can see what their values are above. Multiply them all together. You get 2 pi. If you add them all together, you get 0. And if you square them first and then add them, you get negative 4 pi. This has a combinatorial arrangement with a circle, a balanced point at the middle, and a projection of a sphere, 4 pi, the surface of a sphere, projected, negative. right? It also maintains a twin and a reflection relationship and two pairings. This is like the partition relation here is the most elegant thing you're ever going to see. We're connecting a summation and the product of our j's. So the sum of j's squared and the product of j's squared are identical, except for the factoring of negative pi on the sums. That's beautiful. Really beautiful. Okay, continuing though. And I don't want to scare people with the math, but if you look at the math, it really is worth your time to look at the structure that the math is trying to convey, because the relationship in the math is telling you how nature is structured, is telling you literally what's going on. So avoiding the math is avoiding the conversation.